Well, when you have two interesting mathematical operations, which we do, we have the divergence and the curl, then one of the things that math people are tempted to do is combine them. What happens if you let them interact with each other? And let's realize right away, one of the interactions is not valid. You're going to have some homework, I think, that asks you to figure out what's valid and invalid with some different operations. We'll look at one together. Ask yourself, is the curl of the divergence of f, is that a valid operation? And the answer is no. Why? Because the divergence of f gives you a scalar, and you can't compute the curl of a scalar. This needs to be a vector field inside. So we can't compute the curl of the divergence, but we can compute the divergence of the curl. And of course, being the curious budding mathematicians that we are, we're curious what that is. So let's do it. So the divergence of the curl, in symbols, this is del dot with del cross f. And so this is going to be del dot with, let's write down the generic cross product. So what is this? This is r partial y minus q partial z, p partial z minus r partial x, and then q partial x minus p partial y. I'm just writing down the curl of my f here. And now I'm going to go ahead and take its divergence. And so I get partial x of this guy, and I just get, let's write it down, r partial y partial x minus q partial z partial x plus partial y of this guy. So p partial z partial y minus r partial x partial y plus partial z of this guy. So q partial x partial z minus p partial y partial z. And then I say, wait a minute, I assumed nice things about my function, which means Kleros Theorem applies. And so I'm able to say, hey, r partial y partial x is the same as r partial x partial y. Those are the same. They're opposite signs. They cancel. These are the same. Opposite signs. They cancel. These are the same opposite signs. They cancel. And so the point is we get 0, not the vector 0. The divergence puts out a scalar. So this is the scalar 0. And so since we did that in general, we actually just proved a theorem. We proved that if the components of a vector field f have second order partials, have not have second order partials, have continuous, sorry about that, continuous, I'll have to squeeze it in here, second order partials, got it in, then in general the divergence of the curl of f is just the scalar 0. So I thought I'd do an example with you of the kinds of questions where this can be useful. So here's a question. Does there exist a vector field G such that the curl of G is given by this? And it's like, well, I don't know. That's random. But it turns out that we have all the tools that we need to answer this. So let's go ahead and work this out together real quick. So let's just go ahead and assume that it does. So if the curl of G is indeed this vector field, then the divergence of the curl of G is 0. But if so, then that's the curl of G. And so if so, then the divergence of the curl of G is 0. But when we take the divergence of this vector field yz, xyz, xy, we don't get 0. We get, I think, xz, which is not 0. So we can conclude, so no such G exists. All right, there is no G where curl of G is that. Now that seems like a tricky problem, but it's nice to be able to conclude that. All right, the last thing I want to do in this lecture is deal with the case, what's the connection between our old formula for telling when a two-dimensional vector field is conservative and this new formula for telling when a three-dimensional vector field is conservative. So three-dimensional vector fields are conservative if and only if its curl is 0. What does that have to do, if anything, with the case when f is two-dimensional? Well, here's what you do. You actually can think of any two-dimensional vector field as a three-dimensional vector field in the following way. You have p, q, and then you put 0 for the third component. And so now in this case, we can say, okay, curl, let's actually say it as a statement. F is conservative if and only if the curl of F is 0. Let's compute the curl in this case. So I'm just going to write partial x, partial y, partial z above here. And I'm going to say, okay, the curl of F, what is this? Well, first I'm going to get partial q partial z, so q partial z, subtract 0. That's fine, I can handle that. Then I'm going to get negative, and I'm going to get 0 minus p partial z. So minus, oops, I need to write this, minus p partial z. And then I'm going to get q partial x minus p partial y. Oh, there it is. Q partial x minus p partial y. Now, let's think carefully. We're actually assuming that this F is two-dimensional. So we know something about P and Q. There are no Z's in P and Q. So Q partial Z is 0 and P partial Z is 0. And so our curl is just 0, 0, Q partial X minus P partial Y. And so we can see that the curl of F is 0 if and only if our old formula Q partial X equals P partial Y. And somehow it's nice to know that it's actually the same. It's not a different formula in the two-dimensional case or the three-dimensional case. Same thing happening, and that's how you view the connection. Well, you've got everything you need to tackle the homework from 13.5, and like I said, I'm trying to buy you some time for 13.6 and 13.7 so that we have a good foundation for the last bit of this chapter. We're going to make it. You guys are doing great. I really enjoyed hearing from you in all of your emails, and I'll be in touch.